Yeah. So let's begin. Welcome all. Welcome to the lecture 9 of this workshop, which is on Introduction to MATLAB. So in today's class, what we will be doing is we will look at various chemical engineering problems which involves ordinary differential equation as a part of its model, and then we will code it out that problem into the MATLAB programming and find its solution through the numerical methods, right? So in the previous lecture, what we learned was what are different ordinary differential equations and how we can find the solution to this ordinary differential equation with the help of MATLAB programming, right? So if you recall, the last lecture was about this only, that we learned what are different types of ODE, what are the basic methods that are available, what are the different solver options which we have in MATLAB, and then we looked at the example of unsteady state CSTR, right? Now we will continue this part in today's class where we will look at some more examples which involves ordinary differential equations in its model, right? So let us begin. So we have first problem, which is for plug flow reactor with pressure drop. So we have been given a scenario that there is a gas phase reaction where two components A are producing one component B. Okay, it's carried out in cylindrical plug flow reactor. The reaction is elementary with rate constant K given as 0.05 liter per mole per second. Now see, the reaction is elementary, so the order will be equivalent to the stoichiometric coefficient of your reaction, right? So it's a second order reaction. You can also deduce that from the K unit. So it's a liter per mole second, right? So that is for a second order reaction. Now the feed is pure A with a molar concentration of 0.5 mole per liter. Volumetric flow rate is given, which is 10 liter per second. Initial pressure value of 10 atmosphere is also given. Reactor diameter is 0.5 meter. The reaction mixture has a viscosity 0.001 Pascal second. The pressure drop in the reactor is significant and follows the given equation. So that equation is given, one equation is given to us. We have to model the conversion and the pressure as a function of reactor volume up to 500 liter part. Plot the conversion and the normalized pressure drop versus reactor volume. Compare the exit conversion with the case where pressure drop is neglected, right? So we have been given two conditions like that we have to find the change in the conversion as well as the pressure drop or the normalized pressure P by P0 with increase in reactor volume. And what happens, what is the concentration when we don't have any pressure drop? Now it's a plug flow reactor. So if you will recall your reaction engineering fundamentals, right, and try to model the plug flow reactor, this is how it goes. So the governing mass balance equation, you write it in this form where differential of your conversion with respect to volume is given as minus RA by FA0. Here, rate of reaction is K times Ca square. K value is provided to us, right? It's a 0.05 liter per mole second. Okay. We have been given, since it's a gas phase reaction, right? So it's a gas phase reaction. So as the reaction will proceed, the volumetric flow rate will also change, right? So that change is given by V is equal to V0 into the ratio of the flow rate into ratio of the pressure. Okay, here we are considering the isothermal operation. So if you will compare PV is equal to nRT, so okay, right. So basically you are comparing that and then uh, equating in versus outflow, then you will get this relation. Okay, we can write the total flow rate with respect to the inlet flow rate in terms of this equation, right? That Ft is equal to Ft0 into 1 minus 0.5 xa. Why 0.5 xa? Because the two A are reacting and producing B. Okay, so it's xa by 2, so that's why half. Ft0 is nothing but your Fa0. Therefore, concentration Ca is given by Fa by V, where your flow rate is changing as Ca0 into 1 minus xa divided by this. So this f by v term and the 1 minus 0.5 xa into p0 by p. Right? Got it? So you substitute this two part and you will end up with the Ca value. Right? That's nothing but just a simple mass balance that you have to do. Now here once we know the Ca, we can put it into the PFR equation, right? So we can find the rate Ra is equal to Kca square. So then we can know what will be the next conversion with change in the volume of your reactor, right? Then pressure drop in the reactor, back reactor is modeled by this equation where dP by dV is given as minus beta 0 into the ratio of pressure, temperature and the flow rate. Here again if you will use this relation Ft is equal to Ft0 into 1 minus 0.5 xa, you will end up with this part. Since we are considering the isothermal reaction, T by T0 is 1, right? We have been given that consider beta 0 is 0.01 liter, Pascal per liter. Now, here one thing that you guys have to understand is this is an reference arbitrary example, right? So some values may not make sense, but I am putting it to just give you guys an idea what kind of different scenario you can think about and how you can put it. Like the case here, the pressure drop in the reactor with change in volume is given by this equation. So it's an arbitrary equation. Actually, if you will like to look at into the pressure drop into the packed bed reactor, then you have to use the Ergun equation, right? So if you will search pressure drop in packed bed reactor, right? So its primary Ergun equation, and that equation is given as not here. I think Vicky Log will give a better answer. It's not. Let's open this. Yeah. So it's given as delta P by L. And since it's a packed bed column, it will depend upon the packing parameters also, right? What is the porosity, what is the void fraction, etc. Okay. So this is a different scenario. I mean, this problem that we are solving is an arbitrary problem, right? So we will be using the equation what has been given to us. uh, while you are modeling the actual system, you have to consider the all the equations which will govern your process, right? Right now, this is just a reference problem. Okay, so this information is given. So here we have two things. We have change in pressure with respect to volume, dP by dV. We have change in concentration with respect to volume, also dx by dV. Right? So these two information we have, and then we have been asked to model this. Right? So what I will do first is we will create one function which defines the uh, PFR ordinary differential equation. So it computes the dx by dv and dp by dv, right? So I will write, so this will be function defining PFR equations. So it's a function. Let me say I am calling it as dy by dv is equal to PFR ODEs. Okay. Sorry, function. Yeah. Now, here, what will be the input parameters, right? So, input parameter first is obviously your volume, the dependent variable, independent variable. Then your dependent variable, I am calling it as vector y, right? So, what will have vector y? So, vector y contains dependent variable. So I will say that y comma 1, this one is my conversion xa, and the second element for my vector y is my pressure. Right, just two information I'm putting. Okay, so while you are running the code, we will call it. Okay, so we will take out the information from vector y, update the this information. Okay, now we have been in vy. What else do we need? So either here is anything else changing with time? Probably not, right? CA0 is fixed, K is fixed, P0 is fixed, V0, etc. is fixed. Okay. So let us say I'm just defining it in terms of these two equation and see, let's see how it is being affected. So first I have to find the dx by dv, okay, which is given as minus r by fa0 by r is k1 ca square. So first you have to find the ca value, okay. So ca value we can find it by ca is equal to, where you have to compute this equation ca0 into 1 minus x. Okay, so you have 1 minus xa divided by 1 minus 0.5 times x. This entire thing into p divided by p0. Now here we have not defined what is ca0, p by 0, etc. Right? So either what you can do is that you can write them, provide these values as a input to your PFROD. So if I write ca0, so right now you can see it's showing this red part, okay, this red line, meaning there is some error because these values are not defined. Once I do that, right, so it will update this value p by p0, might be missing brackets. What happened? This is correct. Yeah, sorry, 0.5 times xa. But apart from that also, if you don't define this, right, then also you, right now it's not showing an error, but ideally it should show the line that your ca0 and p0 values are not defined. Okay. Else, one more thing that you can do is you can create a global variable which is referred as global. I define global ca0, p0, ca0, p0. What else information we will need? As of now, I think this we will update as we go ahead, right? So when you are defining variable as a global, so to whatever places these global variables are defined, their value will remain same throughout, right? So you don't have to update their values or provide them as an input. So we are following this strategy. Now, once you have CA, which is given by this equation, you can find the rate. Okay, RA is equal to your K into C square, right? K is also a global variable, so I can put it K here. So I have two global variables defined. Now, my dy by dv, its first component will be rate of reaction divided by F is 0. Yeah. So F is 0. F is 0 is also one variable that I have to keep. So I will write it as F is 0. Right. Now moving towards the second component. So second component of my differential is dp by tv given as minus beta times p by p0 1 minus 0.5 times x. Okay. So I will write dy by dv. I am putting it directly since it's a one equation only, which is minus beta into p0 by p into 1 minus 0.5 times x. Okay. Now here beta is also one global variable. So let's define it here. Right. So this creates my ODE function for PFR. We will save it as PFR ODEs. Then let me create a new file which shows PFR calculation for gas phase reaction. First, remove all the variables, clear the window. Now, first thing what I will do here is I will create a global variable which were same defined in this part. Right? So copy paste this global variables are created. No, that's fine. Yeah. Now I can define this values CA0 as 0.5, this much mole per liter. Then you have P0 as 10 atmospheres. P0 is equal to 10 percentage at atmosphere. Right. Then FA0. FA0 value is given as so FA0 will be your V0 into CA0. You don't have to write it. CA0 into V0. Okay. This many mole per second. V0 value also you have to put, which is given as 10 liter per second. Right? What else? Diameter and viscosities are given, but we are not looking at that. We will first just look at the variation with respect to volume only. Right? You can consider volume as area into length, and instead of looking at the variation with respect to just volume, you can convert it into length and look at the variation with length. Right? Viscosity data, do we need it in our equation? No, viscosity information we don't need it. Right? So this is that. Yeah, beta value. Beta value is 0.01. This much Pascal per volume, Pascal per liter. Let's keep it as atmosphere because here also we are using the same unit, atm, right? So that we are consistent with the units. Once you do that, all the informations are ready. Now let's say create volume vector, right? Which goes from 0 to 500. Let's say at an interval of 10 or maybe 50. right? This much. So volume changes to this way. This will become our span, the initial value. So CA0 becomes our initial value, right? And P0 becomes our initial value. So my Y0 is initial value, that is CA0, then bracket P0, correct? Now I can find the solution which says Y versus V is equal to ODE 45. I have to provide the function which is function of x comma y, right? I'm calling it PFR ODEs, right? The span that you have to give, that is volume, initial value that you have to provide is y0. Okay, let's just run this portion and see whether we are getting the correct answer or not. Okay, let's run. We have got some error which is ODPFR not enough input argument. Why? Just let me quickly look in this. We did this. R is equal to minus QC square. Oh, yeah. So here, since I'm calling the PFR OD, I have to also write, since I'm calling them by a function, you have to write volume and by value. Like you have to call every value, then only you can run it. Still some error, unrecognized variable V. This is volume and Y. V comma Y. Here it's V and Y. Yeah. Now it should work. Hmm. Sorry, there are certain syntax errors which I keep forgetting because I'm using multiple language. I have to keep referring to which indice means what. Right? Vy, yy, and y0. Mm. PFRODs, y is not defined specifically. Here y is defined as y0 is CA0 comma B0. Vy is defined as OD45 V comma Y span volume Y0. Here I don't write it, so PYK CA0 F0 beta 0 P0. Still an error. Mhm. No, this is not a correct syntax. Oh yeah, I realize it. So here we have not specified the dimension of dy by dv. So I have to define dy by dv in this way. Rather here what I did was I defined dy by dv as first and second component. But since we have not assigned the value yet, you cannot write it in this manner. Okay. So this becomes, so this is your dy by dv. It's given as this part. Okay. So your output will be this way. So I can call it now and put it and then it vector with one variable and returns vector of length 1, but the initial length condition. I'm really sorry why this is just an PFROD returns vector of length 1, but the length of initial condition of vector is 2. The vector return and the initial condition vector must be the same number of elements. So my y0 is row matrix, okay, and PFROD is column matrix. Maybe that's why. Okay, now let's see. Not this one. This one. Okay. Again, I'm making some sort of a mistake which we define divide this. Yeah, I realized it. Okay. Where I'm making mistakes is this. One is defining the span that we should put. Okay. That was one thing. And rest I think should work out without an error. If not, then let's me put it this way. This is also defined in terms of the same vector. Okay. Right now I'm getting multiple errors which should not occur because Vy function is defined in two form, V and Y. Y1, Y2 are taken out. You compute this, dy by dx is written in form of this way. We are doing the same thing, right? So till this point we are correct. Now here, clear all, we are defining the global variable, that is fine. Volume boundary is created 0 and 500, right? So here this information is given. V span is created. Y0 is written at 0 comma P0. Okay. Initial condition. Yeah. Okay. This should be 0 and P0. Then you are calling V Y which is calling ordinary differential function PFRODs by the span and y0 value. Volume and y0. Okay, so here is the mistake that PFROD is returning the just one value, PFROD, but rather it should return two values, dy by dx and d. Okay, and why it's not defining that function dx by dy? I'm really confused here. It should work, just not able to figure out what is this syntax error that we have. Everything is referred in a correct manner. The OD is not working. Why? If I just write it this, it will throw an error. Okay. Function dy by d. So here the issue is occurring because the OD somehow is returning only one variable. Uh, so the output of our OD function is dy by dv, which is a vector of two components, right? Minus rf by f is 0 and its beta vector. But somehow it's not identifying it and giving us the wrong result. So if I run the PFROD, it is giving me only one answer, which should not happen because it should have computed the both values. Okay. Can I display? Let's do some troubleshooting and figure out. Yeah, it's only taking one value as information. Dx by dv is equal to then dp by dv is equal to the second term. Dx by dv and the dp by dv. Okay. Let's see. Nope, still incorrect. Hmm. Okay, let me check this and re-verify it. I'm not able to figure out what exact syntax error is causing this because everything appears to be same the to the reference value that I had done previously, but apparently we are just getting one value only. Yeah, what we have to provide is yk. So if I run this command, this code, yeah, it's working well. But for here, I don't know why it's not giving me the correct answer. So in this PFRODs, I have to call this whole thing. Yeah. See, so in this two vector we are getting, the vector we are getting. But the current PFROD that we have written, it does not provide that information, which is very weird because it should have, without any hesitation, corrected the data. Anyway, let it be. So once you define, let's say you have defined this ODE, then the next step is to use an ODE function to solve it, right? So I will take the reference example here. So here we have defined PFR ODEs. We are providing the V1 and the Y0 value, okay? And then this ODE solves the vector, then you get the X and pressure value, okay? That is from Y vector. So first column will give you the X value, second column will give you the pressure value, then you compute the P ratio. I am plotting the graph in one plot only. So I one on the left side I will have the conversion versus volume. On the right side I will have the pressure versus volume. Okay, this is just some customization. Now we have been also asked to find what will be the exit conversion if we don't have any pressure or pressure is negligible. So for that, the delta P equation, which is dependent on the beta factor, right? So you consider it as zero. If you consider it as zero, then the beta value will go down, right? Beta value will, so this dP by dV will become zero. Okay, so you won't have any pressure drop in that case, right? And so we are doing that, and that is also so for that zero beta value. So here beta is turned to zero, and then we are finding the solution. Okay, yeah. And when I run it, this is what you get, that you have conversion. Okay, the left curve. So it's increasing with the increase in the reactor volume, and it's going towards the plateau. Now, when you have when you don't have any pressure drop, so this dotted line shows how the conversion will vary. So conversion occurs much faster because you don't have any pressure drop in your system. P by P0 decreases drastically, right? So you can see with for a 500-liter volume, the almost 60% of pressure drop has occurred. Okay, right? So this is one part. Now let us look at the second example. I will verify this part why it's not exactly working. I'm not able to pinpoint that error. Sure, it will be some small syntax error which I cannot see currently. But apart from that, I don't think so anything else fundamentally we have done wrong. Right? So let me see. If I will find it, I will just update it and write it down. Okay. Then the second problem is on co-current heat exchanger. So in the co-current heat exchanger, what information we have been given is that we are designing a double pipe co-current heat exchanger to cool a hot process steam with a cold coolant stream. Hot stream data is given, its flow rate is given, inlet temperature is given, CP value is given. Cold water or the cold steam flow rate, inlet temperature, as well as heat capacities are also given. Exchanger information also we have, which is heat transfer coefficient. Heat transfer area per unit length is also given. This is based on tube diameter that we have written. And the total length of exchanger, which is 10 meter. Now, what we have been asked is we have been asked to determine the outlet temperature of both stream and the temperature profile along the length of the exchanger, yeah, and calculate the total rate of heat transfer that will occur. Right now, so if you will write an energy balance equation, okay, between the uh, stream and the heat transfer that is occurring through the exchanger. Right? So in that case, you can write it as mCp delta T is equal to UA TH minus TC, right? Here, mCp delta T shows change in the stream, change in the energy of any stream, will it be hot or cold stream, right? And that heat is transferred via the tube. Okay, so that's why the UA delta T heat transferred via the tube will be equivalent to what is the fluid temperature that is changing at a time, right? Now this equation we can here area, since we have been given area per unit length, right? So you are writing this area is written as AL into DZ star, where AL is the area per unit length. Once you have this information here, so this particular energy balance is done for a smaller fraction of your system, right? For overall fraction, you will get the MCP delta T1 minus T in minus T out as UA TH minus TC. Okay. So instead of TH minus TC, actually you will have sorry, the LMTD. So what we put in the overall heat overall driving force, which is given by delta TLM, right, for a heat transfer coefficient, for a heat exchanger problem. But if I consider the smaller element, So at that particular smaller element, heat transferred from hot to cold fluid will be equal to UA TH minus TC, where TH is the hot fluid temperature instantaneous and TC is the cold fluid temperature instantaneous. You expand area into AL into dz, so that I can find dt by dz as UAL TH minus TC divided by MCP if. Okay. Now, depending upon what temperature you look, this equation will vary. So if I'm looking at the change in the temperature of cold fluid, right? So cold fluid temperature is increasing. So this will become the differential of tau Tc divided by dz is equal to UA TH minus TC divided by MCP for cold fluid. So since temperature is increasing, this entire term is positive. If I look at the hot fluid temperature, so this delta TH will be the negative part, right? So to account for that negative part, here I have to put a negative sign in minus UA TH minus TC divided by MCP for hot fluid, right? So this gives you the profile of temperature along the length of your tube, right? So these are our ODEs, and what we have been asked, we have been asked to find the profile of temperature along the exchanger length and calculate the total rate of heat transfer. Okay. So this is our example. Should I do it directly, or maybe we can do it and then last problem you guys can try it out on by yourselves, right? So let's just code it out and see how it works. So in class, this is co-current heat exchanger problem. What information we have been given, I will write them down. Given data. So what data we have? We have MH as 2 kg per second. Cp of H given as 2.1 percentage kilojoule per kg Kelvin, right? Then you have THN as 120, okay, degrees C. Same way I have cold fluid flow rate 1.5 kg per second. Cp of cold fluid given as 4.18 kilo, sorry, there should be kilojoule per kg Kelvin. Tcn is given as 25. Right? You have overall heat transfer coefficient U as 350 watt per meter square second. Then area per length is given as 0.2, this much meter square by meter, and the last total length L is given as 10 meter. Okay, so this is the given data. Defining CSTR, not CSTR, sorry, heat exchanger, ODs. So heat exchanger OD is your, it's a function of Z. Okay, so you have to write this part. Function of your independent variable, which is I'm referring it as Z, or you can refer it as, let's say we are referring it as small l pH comma Tc, and what will be my function? That is U into area per length into Th minus Tc divided by, if I'm writing with respect to, so let's say first will be, we will write a DTH, first row will be DTH and second row will be DTC. Then I can write MH into CPH, correct? This entire term will be negative, okay? Then you have similar term, but here you will have MC, CPC, okay? And obviously it's a positive equation. You have that. Now I define the length span, which is L2 length. L span is given by this. So we will solve the ODE, which will provide you L, comma T values. That is nothing but ODE 45 at the rate function of length, comma temperature. I'm calling it heat exchanger ODE. Span is given as L span. Initial value, so what initial value you have? So that is your TH in, comma TC in, okay. Okay, let's run it. Okay, maybe I'm making some mistake in defining ODs today, which I'm not able to track what exactly I'm doing wrong. These are the ODs defined as. Oh yeah, sorry. This we had already mentioned. This is my mistake, that I have to write the function of T. This will become T1, T2. Okay. Here your T is equal to TH bracket TC. This is your ODE. So this is my mistake, because yeah, obviously we had previously also discussed that the solvers considered that you provide dependent variables in form of one vector only. Okay, now let's see and run whether we haven't got rid of the error. at the rate z comma y. I've written down the alpha beta into y1 y2. Z span is also given 0 to L. Y0 is also given. Oh, was I giving a wrong syntax? If I do keep this, then I'm getting an error. Okay. I realized it. So we did not need to provide at the rate function L and T. Okay, we just have to put the equation here, the supply the ODE because it's already defined what are the L and T values, right? So that will be computed. So that's that. Then once I have done it, I can find TH is equal to T, comma, the first column, the first row or first column. Yeah. It's a column vector, right? So T, comma, all row, first vector. TC is equal to T, comma, all row, second column. You can plot them. Plot. You have to define one length vector also, or length is already calculated. L versus TH. I will write color is equal to red. Then this one is blue. Okay. Hold on and let's run it. Now what happened? It increased into 93 and TH is yeah. Still making some error. Mm. It's computing everything correctly. Still, somehow we are getting the wrong information. Oh, okay. Yeah. I'm making mistake here. So it's 350 watt per meter square Kelvin. This is U. My area is this. This is also in Kelvin. So this much watt I will get. While for MCP delta T, the values are in kilojoule. Okay. That's why the answer is not correct. So instead here I have to do is not 250, it's 0.35, 0.35. Yeah. Yeah. Now the values are correct. So this is TH, which is decreasing, TC is increasing. Okay. Then we can also find F printf overall heat transfer is equal to, I can do display. You can write MC into CPC into TC in minus this TC vector and its end value I will put, right? So this will show the overall heat transfer coefficient. Sorry, overall heat transfer. This much, right? So this much kilowatt heat, sorry, this much kilojoule heat transfer had occurred, right? So same thing you can go through this reference example also. Obviously, I have here highlighted them very nicely. Okay, so you get this sort of a curve which we are getting, and then this is your overall heat transfer coefficient. Sorry, overall heat transfer values and outlet temperature of TH and TC. Now coming back to this PFR equation once again. So do I, if I let's say don't provide it, will it correctly compute? No, it's not recognizing the variable. Yeah. Still not clear why this is happening. This error, I have to sit and figure it out. Again, it will be some, as I was mentioning repeatedly, it will be some sort of a silly mistake which we might have made and we are not able to catch it right now. So if you can see something directly which I'm doing wrong, just let me know. Or I will just look at it after some time with a fresh mind and then update you, right? So this were the two example. And the third example, since we are out of time, you guys can try it on your own, which is on the unsteady state CSTR, which we have previously solved also. So here we have multiple reactions ongoing. we have been given the rate constant, initial concentration, feed data, reactor volume, etc. Okay, the reactor startup is critical. We have to simulate first 16 minutes of the operation. We have to plot all the concentration versus time, determine where the maximum concentration of C is reached at what value, right? And what is the yield point. Initial condition is given that reactor is initially filled with the pure solvent. So all concentration are considered zero. Then, I mean, at equal to zero, the reactor filling might start, and then you have to find how it's changing with time, right? So these are the governing mass balance equation. You have dNA by dt, dNB by dt, dNC by dt, and this. So everything is given in terms of the feed flow rate and the concentration and the reaction rate, right? Reaction rates are also given. So last time when we did a PFR, did the CSTR example, we included both mass and energy balance. In this example, we only had to include the mass balance, but the mass balance will include four components of A, B, C, and D. And for each, you have this governing equation ready. Okay. So create a function, select the time which is in your independent variable 0 to 16 minutes, plot out the value and see how it varies with time. So ultimately what you will see initially, as soon as you at equal to 0, since everything is 0, both CA0 and CB0 will start increasing, but uh, A and B are both being consumed in first reaction. A is also being consumed in the second reaction, right? So you will find that they are increasing, but then again they will start decreasing, and and then we'll reach some sort of a plateau region. Okay, C and D will start increasing afterwards, after A and B concentration has built up, and then it will go down. So if I can just show you directly, yeah, here. So here first define the CSTR ODs, which I have defined in terms of the N and this functional parameters, right? And we have written these values. Okay. Then in this part, I'm just solving the CSTR OD and then finding the values. So if you run it, yeah, this kind of a concentration profile you will get. Since A and B are the reactant which are being added, its concentration increases drastically. But after some time, A is being consumed more, so its concentration reaches to some steady state. Similarly for B, and C and D are being produced, so they are reaching. And after some time, you will reach a steady state. Okay, there your gradient will become zero. Correct? So this is one aspect. Do look into it. You can directly do it, or you can just refer to this code also. Okay, but try it out on your own and see how you are getting your answers. Okay? I will just update you on this, and that's it. So this is it for today's class. The PFROD issue, I will look into that and update you.